Problem number 4 is giving you two parallel conducting plates connected to a battery. The first question is asking what is the direction of the electric field. Hopefully this is a very easy question for you since we have the negative side of our battery going along the top plate. This is going to have negative charge up here. Since I have the positive side of my battery attached to the bottom, this is going to be my my positive charge, and we know that charges go out of the positive and into the negative, so it's going to look like this. And that is going to be up. In the next part, we're calculating the electric field between the plates. And in order to do that, we need to figure out what information is given. So the first piece of information is that the voltage is equal to 120 volts. And the length of the plate is 0.1. And the distance between the plates is, I'll call that R, 0.05. And then we've got a velocity of an electron of 2.9 times 10 to the 7 meters. Okay, so when we're calculating the electric field, we have the equation E equals KQ over R squared. And we have all of the information given. This R is representative of the distance between my charged plates. So that's that's already given. This is R. And then we've got K. So the unknown here is Q, but what we do know is that we're given voltage, and the equation for voltage is KQ over R. So if I solve for Q here, I get VR over K, and then I'm going to plug VR over K into my equation. And we can see that one of the R's cancel out in the denominator, the K's cancel out, and I end up with voltage divided by radius, which is 120 divided by 0.05, and the answer to that is 2,400 newtons per coulomb. Part B. The next scenario says describe the electron's path when it moves between the plates. So when we have an electron moving vertically, it's going to continue to move vertically at a constant speed. The only force that is acting on it is due to the electric field. So if my if my charge is an electron, that means it's got a negative charge to it, and negatives repel the negative plate and attract the positive plate. So if I'm going to travel to the right with a constant velocity, I'm also going to experience a force downward, attracting the positive and repelling the negative. So this one is going to create a parabolic path. It's actually going to be parabolic as soon as it enters. So let me accurately depict this. It's going to enter and immediately start falling as it experiences that electric force downward. Okay, what's the direction and magnitude of the electron's acceleration? If we draw a force body diagram, the only force acting on it is the electric force downward, and it is experiencing the electric force of the positive plate attracting it and the electric force of the negative plate repelling, but they're both in the downward direction. So we just can call it a downward force. There's no actual force pushing it to the right. It's just moving right due to constant velocity and inertia. And so the direction of acceleration, since force is downward and F equals ma, then A is also going to be downward. In terms of the magnitude of the electron's acceleration, for this problem, we are going to use our F equals ma equation. I already wrote it out here. We know that the electric force is equal to mass times acceleration. The electric force is given by electric field, which we got from part B, times the charge of our electron, equal to the mass times acceleration. So A is equal to EQ divided by M. And it may seem like we don't have those values for the charge and the mass, but that's in your equation sheet. So look for that in your equation sheet. We've got 2400 from part B multiplied by the charge of an electron, that's 1.6 times 10 to the negative 19, divided by the mass of an electron, 9.11 times 10 to the negative 31. And the answer for acceleration is 4.2 times 10 to the 14 meters per second squared. Now it's asking, will the electron leave the space between the plates? In this scenario, it's basically projectile motion problem. So we have an x component where velocity is constant and it's moving at 2.9 times 10 to the 7 meters per second. We've got an acceleration of 0 in the x direction. We've got an initial position of 0. And I think that's it. The y component has a downward acceleration, so we can call it negative 4.2 times 10 to the 14 meters per second squared, since it's downward. We also have initial position, so let's call the initial y position. You can define it however you'd like to. I defined the 0 position to be here. So that means that the initial y position is going to be half of 0.5, so, or half of 0.05. So then that gives me a initial position of 0.025 meters. And then we want to find where the final position is equal to 0, because that would be where we want to see if the electron is leaving the space between the plates or is hitting the plate. The time is what we're solving for here. We always solve for time in the y component, and then we plug it in for the x component. So in this scenario, we can use our equation y equals y naught plus v naught t plus 1/2 at squared. My initial velocity is 0. My final y position is 0. So I have negative 0.25. Sorry, I need to add the 0 in front of that. 0.025 is equal to 1/2 the acceleration from part D times time squared. And then when I solve for t, I end up with, put that negative in there so the negatives cancel out. I end up with the square root of, if I multiply the 1/2 to the other side, I get 0.05, again, back to our normal length, divided by 4.2 times 10 to the 14. And the time ends up being 1.09 times 10 to the negative 8 seconds. And then I need to solve for the final position when time is equal to 1.09. So I'm going to use x equals x naught plus v naught t. I know that the 1/2 at squared cancels out because acceleration is equal to 0. My initial position is 0, so x is equal to 2.9 times 10 to the 7th times a time of 1.09 times 10 to the negative 8th. And I get a 0.31 or 0.32 meters. And when I compare that to the position here, as it's being launched, 0.3 meters is going to be all the way out here. So the projectile is actually going to land past the plate, which means that our answer, will it leave the space between the plates? Yes.